Greetings and salutations. As we begin learning about vectors, there are two key concepts which we need to understand and be able to visualize. What is a linear combination of vectors, and what is a span of a set of vectors, and how do we visualize the span of a set of vectors? Understanding these concepts will be important for the rest of the semester, and being able to visualize them will allow us to visualize more difficult concepts that come up later. Let's start by looking at some vectors in R2. Here's a red vector, 2, 1, and a yellow vector, 1, -1. If we start with the red vector, one thing we can do is scale the vector. Multiplying it by 2 will make it twice as long. Multiplying it by -3 will make it 3 times as long, but pointing in the opposite direction. We can also scale the yellow vector. Notice that scaling a vector does not change the line that the vector lies on. We can also add the vectors together by putting the tail of the yellow vector onto the tip of the red vector. The resultant is this blue vector. Notice that the coordinates of the blue vector are the sum of the coordinates of the red and yellow vectors. We can combine these operations. By scaling vectors and then adding them together, we form linear combinations. For example, we can start with the red vector and scale it by a factor of 2. Then we can take the yellow vector and scale it by a factor of 3. If we add these two scaled vectors together, we get a blue vector. This blue vector is a linear combination of the red and yellow vectors. By scaling the red and yellow vectors in different ways and adding them together, we can get various linear combinations. The coefficients in front of the vectors are also called the weights of the vectors, and they don't have to be integers. Even just scaling this red vector to make this orange vector counts as a linear combination, because we can just treat the weight of the yellow vector to be 0. To make this more formal, a linear combination of vectors is any other vector which can be formed by scaling the original vectors and then adding them together. All of the possible linear combinations that can be formed is called the span of the set of vectors. These are all of the vectors which are sums of scalar multiples of some or all of the vectors in the set. Let's look back at our example in R2 and the red and yellow vectors that we started with. We can visualize the span of these vectors as a grid that is formed by the red and yellow vectors. Let's look at the linear combinations that we saw earlier and see how they fit on this grid. Notice that the blue vector is 2 grid lines in the red direction and 3 grid lines in the yellow direction. The purple vector is -3 grid lines in the red direction and 1 grid line in the yellow direction. This matches up with the weights that we use to form these linear combinations to begin with. Since this grid covers all of R2, this means any vector in R2 can be formed as a linear combination of the red and yellow vectors. So we would say that the span of the red and yellow vectors is all of R2. Looking at another example in R2, what if we start with two vectors that are already collinear? Now any linear combination of these vectors would just be another vector which is already parallel to these vectors. This is further visualized by imagining the grid formed by these vectors, which would just be a straight line to the origin. This is an example of two vectors whose span is not all of R2. Looking at any two vectors in R2, we can form a grid. And most of the time, that grid will cover all of R2. If the vectors change, the grid changes with it, but still usually covers all of R2. However, if these vectors are collinear, the grid will not cover all of R2. By thinking of this grid, we can now visualize the span of two vectors in R2. Now let's look at some vectors in R3. And again, we'll start with two vectors, a red vector and a yellow vector. In the same way as before, we can scale these vectors and add them together. And this forms linear combinations of these vectors. Now, it can be difficult to visualize these linear combinations because our computer screens are two-dimensional, but let's see what this looks like as we rotate the vectors. If you notice, all of these vectors are lying on the same plane. At certain angles, they all seem to line up. We can draw this plane and see that the vectors really do lie on a single plane. This plane is the span of the red and yellow vectors. This means that the span is not all of R3. And we can also see this by drawing this green vector, which is a vector in R3, but not in the span of the red and yellow vectors. There is no way to add the red and yellow vectors together or scale them in a way that makes the green vector. If we wanted to make the green vector, we could add a third blue vector to our set. Now we can use the red, yellow, and blue vectors to make this green vector as a linear combination. This blue vector adds a third dimension to the span because now we can move out of the plane. If we were to form a three-dimensional grid using these three vectors, it would span all of R3. Let's finish up by talking about some of the takeaways from this video. First, a linear combination of vectors is formed by scaling the vectors and or adding them together. The collection of all possible linear combinations is called the span of a set of vectors. The span of a single vector is just all the ways of stretching that vector, and would just form a line through the origin. We saw that the span of two vectors would be a plane unless those vectors lie on the same line. And the span of three vectors would be a three-dimensional region, unless those vectors lie on the same line or plane. Being able to visualize vectors in 2 and 3 dimensions can help us understand what it means for vectors to be in higher dimensions and what their spans might represent. Hopefully, by watching this video, you now have a better understanding of how to visualize linear combinations and spans of sets of vectors, and you can use this to further your understanding of the material throughout the course.